to determine the derivative of f at t of the function f at t equals root t. Okay, so we start it the exact same way, f prime at x, or should be f prime at t equals the limit as h approaches 0. Okay, now let's actually write root t plus h minus root t all over h. Okay, as soon as you see a root, we know that it's going to trigger us to use the conjugate. Okay, so write the first thing as it is, switch the sign in the middle, write the second thing as it is. Okay, and it has to be over itself because then we're just multiplying again by 1. Okay, the numerator, x plus h minus t. Okay, because root x plus h times root x plus h is just x plus h. The middle two terms cancel, and then root t times root t is just t, so minus t. And this is going to be over t plus h plus root t. Okay, again, a lot of the times the denominator cancels, so don't actually expand it yet because you're just going to have to refactor. These two t's cancel out, the h's cancel out to 1. So now we have 1 over root t plus h plus root t. Let's sum in the 0. So we have 1 over root t plus root t, because this h goes to 0. So we have 1 over 2 root t. And that is the general derivative of f at x, or f at t equals root t. Okay, and just as a note, the domain of f at t equals root t is greater than or equal to 0. And we know that because root t looks like this. Okay, and you can root root 0 just equals 0. Okay, but the domain over its derivative, 1 over 2 root t, doesn't have that bar here. So it's just strictly greater than 0. So just in that, we can see that a function does not need to actually have a derivative through its entire domain. Okay, because this is the start of the function, there's no derivative right at that end. Okay, so example 4. Determine an equation of the tangent to the graph 1 over t at the point where x equals 2. Okay, so we want the entire equation of the tangent. I'm still going to do the general form. So the limit as x approaches, or h approaches 0. And we have 1 over t plus h minus 1 over t all over h. Okay, when we use common denominators, we have to find, or when we use fractions, we have to find a common denominator. So let's bracket this and put the t plus h up here, t plus h over t plus h, and let's put the t here and here. Okay, so we now have t minus t plus h all over t plus h. Okay, and if you remember, I don't like to put fractions over a number, so like 3 numbers on top of each other. So let's just go divided by h at the side, and then what we'll do in the next line is actually flip that and multiply. So we're going to multiply by 1 over h. Okay, it's important to keep this t plus h in the bracket because what we're going to do is expand this. So we actually have t minus h. Those go away. Okay, over t plus h. These h's also cancel out. We are left with negative 1 on the top. Okay, so the limit as h approaches 0 of negative 1 over, let's go t squared plus th. Sum in the h equals 0, so that goes away. We're left with negative 1 over t squared. Now that's the general form for the derivative. If we want f prime at 2, all we have to do is sub in the 2 on the bottom there, negative 1 over 4. Okay, for this question, just a reminder, we want the equation of the tangent. So x equals 2. From the original, f at 2 equals 1 over 2. So we're actually dealing with the point 2 comma 1/2, and we're going to deal with the slope of negative 1 over 4. So if we go y equals mx plus b, 1 over 2 equals negative 1 over 4, 2 plus b. 1/2 equals negative 2. This is negative 2 over 4, so it's negative 1/2 plus b. So 1 equals b. The equation of our tangent, therefore, y equals negative 1/4 x plus 1. And that is the equation of our tangent. So just to note, the normal, so something called the normal to the graph of f at point P is the line that's perpendicular to the tangent at P. And we're definitely going to come back to that once we do vectors. So example 5, determine an equation of the line that is perpendicular, so like the normal, to the tangent to the graph of f at x equals 1 over x at x equals 2. And that intersects it at the point of tangency. Well, from the previous slide, we know that f prime at x, use x, is negative 1 over x squared. Okay, we also subbed in the 2 and we got the point 2 comma 2 comma 1/2. So we want an equation of a line that's perpendicular to the tangent. So the tangent of our slope, the slope of our tangent is negative 1 over x squared. So that means perpendicular, we're going to flip and then make this negative a positive. So our slope now is x squared. That means our slope at the point 2, because remember we're doing a normal at the same point, is going to be 2 squared, which is going to be 4. So our normal is going to have a slope of 4, which actually makes sense because on the previous slide we had negative 1 over 4. So again, it's a negative reciprocal. Okay, we want the equation of a line that's perpendicular and that intersects at this point of tangency, point P. So let's go y equals mx plus b. Okay. 1/2 equals 4, 2 plus b. 1/2 equals 8 plus b. And then 1/2 minus 8 equals b. So let's go negative 7.5 equals b. Okay, therefore, the equation is y equals 4x minus 7.5.